I'd love to tell you more about what my research group, Digital Structures, is working on at MIT. So we are an interdisciplinary group focused on architecture and structural engineering, and most of the students in the group have a similar background to me, either starting out in architecture and then becoming more interested in engineering, or sometimes the other way around. We also have students from a few other disciplines, computer science, mechanical engineering, and what we're really united about and excited about is efficient and expressive structural form. We start with these examples from the past and present, which demonstrate to us not only the amazing formal possibilities that can be discovered when structural principles are playing a central role in design, but also the diversity of such forms. So for us, this shows that injecting performance information into architecture is not reductive and doesn't lead everyone to the same solution, but in fact opens up the possibilities and can expand our formal palette. It's also critical that we think about performance in design because buildings have a really large impact on our changing climate. In this one example from colleagues of mine, they showed that the Beijing Olympic Stadium on the left uses 14 times the embodied carbon per seat of the London Olympic Stadium on the right. A 14x differential would be unheard of in most other fields. And for example, in two cars on the highway, you wouldn't have one that's 14 times more fuel efficient than another. But it's common in buildings, I think, because for too long, we just haven't paid enough attention to performance. We can't afford to do that anymore. We really need to pay attention to how our buildings are contributing or detracting from a more sustainable world. We're also no longer, technology no longer is needed simply to advance the possible. We now have the technology to achieve almost anything in design and construction. So these 19th and 20th century questions of what can we build and how can we build it are no longer so relevant. The key critical questions today are what should we build and how should we build it? These are hard questions to answer, and the way that our typical design processes work make them especially challenging. In a typical design, of course, as we move from a blank piece of paper where anything is possible to something that's ready to be materialized, we gain information and lose freedom. Early in the design process at the very beginning is the key time where technology and performance and engineering information can play a pivotal role in decision making, such as the building's massing, the building's typology. But too often engineering thinking is really just used to validate a concept once it's already been quite formally decided. And so there's often little opportunity for engineering principles to play creative roles in design processes. We're really interested in changing that. Another reason that that's hard, though, is because the two disciplines responsible for these different aspects of design, architecture and structural engineering, are so often isolated and separated from each other, even though they're working literally on the same thing on the design of buildings. For example, in terms of how computation is engaged, in terms of how we think about fabrication and construction, even in terms of how we think of education, so often these two groups are isolated in terms of their culture and vocabulary and ways of thinking about buildings. We think it's really critical that we bring these two fields closer together, which will result not only in more efficient and resource responsible designs and structures, but also designs that are more elegant and that achieve a kind of intellectual richness that comes from this integration. In my group, the way that we often think about how to integrate these two sides of the building design process is through computation, and we use a formal system called the design space. This is an example of a really simple design space for a truss. If I move the lower left node up and down and left and right, we can consider those to be variables or things that we can change in the design geometrically, and they have an impact both on how the truss looks, but also on how it performs, how much material it needs to support the load. And that's visualized by this landscape that we see in blue that represents the change in performance as geometry changes. And in fact, the performance can change pretty dramatically as the form changes. Using techniques that have been around since before I was born, we could find the optimal solution to this problem, the local or the global optimal solution, the truss that uses the least material. But optimization itself is almost never used to design buildings, even though it's been around for a really long time. And that's almost certainly because optimization is insufficient to fully address the wide spectrum of things that we care about in building design, which is almost always multi-objective, part quantitative, part qualitative. Of course, the quantitative aspects of design are important, and I'm arguing critical, but we can't neglect the qualitative aspects of design that make architecture and space appropriate for humans, and that connect to the kind of creativity and experiential qualities that are so delightful in the built environment. And so we need to find some balance between the performance that is critical, but also the human and creative and contextual aspects that are so hard to quantify. One way to do that is to still use this design space concept, but to back up from the idea of optimality. We don't only need one solution. We need to explore a diverse range of solutions that can help us negotiate and balance our different needs. We try to do that through tools and through algorithms. This is an early tool that I developed during my PhD called Structure Fit that generates efficient two-dimensional trusses collaboratively with a designer using something called an interactive evolutionary algorithm. That the computer suggests designs, and then the user selects the ones that are most interesting, and the computer uses those to breed new options that are high performing. And so there's an injection of both human interest and prioritization and computational simulation and performance. And we always think it's important for the human to have the final word. We don't want to use computers to fully automate or optimize, but to enhance and amplify our own creativity and to guide us towards high-performing solutions we may not have found by ourselves. Tools like this can allow us to find some really interesting and diverse options, even just in 2 dimensions. So for example, Structure Fit is able to find designs that were found through other methods and are known to be very high performing, but it can also be used to find these less common designs that are neither obvious and geometrically regular nor optimal, but perhaps that represent the best balance of the many priorities that we have in design, and that can start to open up new solutions that we haven't seen before. What happens when we try to apply these similar ideas to larger and more complex structures? For example, a roof truss like this that has many members and could be generated parametrically using advanced computational geometry. We get lots and lots of solutions, but one of the challenges now is that we actually have too many solutions. Here we have 5 billions of trillions of design options that we could search through. Here we're looking at a minuscule percentage of this design space, and it's really, really hard to start navigating. Even if we use performance, which we always do, to try to filter and guide ourselves through the space, it's just too unwieldy for us to make sense of this design space. And so recently, a lot of my research has been looking at how we can harness advances in emerging fields like machine learning to make complex, large design spaces that are essentially data sets, human legible and relevant for human designers. In this example, we're using something called a variational autoencoder to create a low-dimensional, in this case, 2-dimensional latent space that compresses this 36-dimensional, really large-scale design space into something that is intuitive and responsive, so that a designer can literally click through this landscape to find a very wide range of high-performing options that are quite diverse from each other, that are unexpected, and that all perform well. And so we're able to do that by connecting these emerging machine learning techniques with our goals for creating design tools of the future. In our work, we also look a lot at multi-objective problems. So not only quantifying, for example, structural performance, but also thinking about how to quantify operational energy use. And in many cases, we find that there are interesting trade-offs between these different quantifiable goals that are often only considered independently. And so by starting to use multi-objective thinking, we are able to identify relationships and interactions between different goals and different disciplines that can lead us to better solutions than if we only considered them independently. And then finally, in computational design, we're also really interested in opening up and brainstorming with the computer, opening up the formal palette even further. We use something called structural grammars to generate really diverse and wide-ranging options that all use structural principles in rational ways and that are high-performing, but that also really look unusual and are far away from something that we would be able to create by hand. So this is one example of a grammar to create pedestrian bridges. Here's another grammar that I developed with colleagues that creates equilibrium structures that are very surprising. And so we're really interested in using these emerging techniques to change the vocabulary of efficient structural form and expand beyond what we've seen before. However, you may be wondering, once we start to really open up these new structural geometries and topologies, they start to get very complex. And you might wonder, well, how do you actually build all these? Even if they're efficient and high performing on the computer, they might be very expensive to build. One answer to that is to start looking at digital fabrication, where the complexity, the cost of complexity is reduced because a computer is controlling a machine that is materializing all the parts of the structure. So in this case, for example, a 3D printer is mounted on a 6-axis industrial robotic arm, and it can create a regular lattice truss like this, but it can also create one where every node is different, where every member has a different length. It's just as easy for the robot to do this. And in this case, the shaped structure is driven by structural principles. It's far more efficient than one that has a regular geometry. It's also, I think, a lot more beautiful. And it's just as easy to do this with digital fabrication. And we think there's a lot of promise here that we're interested in exploring further. One sub area within that is thinking not only about morphing a structure to become more efficient, but actually changing its topology, the connectivity of the elements, which often has the biggest impact on overall structural efficiency. But as for many years, even though we've had the techniques to generate optimized topologies, it's been very hard to think about how to construct them because they've been so complex. We've been working together with my group and some colleagues in computer science at MIT to connect state-of-the-art task and motion planning algorithms to the automated path planning for architectural structures. So for example, this topology optimized vault here, we can automatically find the robotic instructions to build it so that it becomes a lot, we are automating and offloading the time-consuming part of figuring out the sequence and instructions for how to lay out all the material, and then potentially even bringing that into the design process. So here's one example where we're creating a topology optimized beam. The sequence for the robot to materialize this has been planned using our system, along with all of the instructions for the robot's location and configuration of all of the 6 degrees of freedom of its joints. And it's ensuring that the structure is stable, not only in its final configuration, but also during assembly, and that it doesn't collide with itself or with the structure. So all of that planning is automated, and we're finding ways to make that faster and faster. This video from a few years ago, it took 72 minutes to run our planning algorithm. Now it's down to the order of a few minutes, and we're hoping that that can eventually be a design input so that we can adjust our structures so that they're easier to build in response to these kinds of algorithms. And then finally, we're also applying our work and our thinking to more practical structures. For example, concrete is an incredibly highly used material all over the world, but especially in emerging economies where a large amount of housing is desperately needed and is being constructed. A lot of times, as many of you may know, concrete is not used efficiently. We don't need most of the concrete that's in most concrete buildings for safe structural behavior. It's just there in order because it's simpler to make everything geometrically regular. But if we can find ways to efficiently and affordably carve material away, we can start to make structures that are far more affordable in certain parts of the world and far less impactful on the environment. For example, in this project in India, we've partnered with a local organization to develop a system for carving away material in horizontal spanning floor systems using some tools that we've developed, and also partnering with an organization to figure out how can we build these efficiently. And in this case, we're using cold formed steel sheets that are laser cut into shapes and then welded together where by experts where there's a lot of local knowledge in how to do this. And we're able to create structures that are high performing, that meet the fabrication culture that we're working in, and all of that can be incorporated into our design tools. So we're using the fabrication information to define our design spaces. We're also working on this in other material systems, for example, in mass timber, which is an emerging and exciting construction system that promises a more sustainable future. We also see that a lot of the wood isn't actually necessary structurally. And so by finding ways to carve away what's not needed, we can both save even more and also open up a new expressive language for structural form. Thank you very much. It's been a pleasure to share this work with you.